Formula One cars are impressive engineering systems, with their 2.4-litre V8 engines having an impressive power output of over 750 brake horsepower and maxing out at 18,000 RPM. F1 cars can go from 0 to 100 in under 2 seconds, reach top speeds of 330 km an hour, and produce deceleration forces of up to 6 G. If you were driving, it would feel as if your neck is about to tear off, while you involuntarily exhale as your lungs hit the inside of your ribcage. Now let's consider the energy carried by the tyres and the work done on the tyres. Massive amounts of energy are transferred to the tyres from the crankshaft, and the work done on the tyres by the acting forces is of great interest. Minimizing wear and degradation upon the tyres is extremely important in modern F1 racing. In this video, I'm going to introduce the concept of work and energy in rigid body dynamics to analyze the tyres of an F1 car, exploring various quantities such as the kinetic energy these tyres carry, how much work is done by the forces on these tyres, and a few other important quantities. This involves using kinematic equations and introducing the concept of mass moment of inertia. As a second-year engineering student, I'm already assuming you have some understanding of energy and how energy is transferred through work. If you don't, I suggest you go and learn or review these concepts before watching this video. We're going to be considering an F1 car starting at rest and reaching top speed in a relatively straight line, where the tyres are assumed to remain rigid. Thus, we can consider the car and the tyres to be in planar motion, greatly simplifying our analysis. The kinetic energy of a rigid body in planar motion is given by the equation T equals a half mv bar squared plus a half I bar omega squared, where m is the mass of the body, v bar is the velocity of the center of mass, I bar is the mass moment of inertia about the body's center of mass, and omega is the body's angular velocity. From the equation, you can see that the kinetic energy of the tyre is going to equal the sum of the tyre's translational and rotational kinetic energy. So from the formula in the previous slide, we need to understand and be able to calculate the mass moment of inertia of a body, which measures how the mass of the body is distributed about an axis of rotation. It's equal to the total sum of the product of an infinitesimal mass element dm and the square of the element's distance from the rotational axis. For continuous distributions, integration is required. This value obviously depends on the geometry of the body and changes if the axis of rotation is changed. Since we're dealing with the tyre, we're going to use the mass moment of inertia formula for a cylinder, I bar equals a half mr squared, where we've assumed that the crankshaft passes through the center of mass of the tyre, which corresponds to an axis passing through the center of the tyre. If we also assume that a point on the circumference of the tyre is traveling at the top speed of 330 km an hour, which is 91.7 meters per second, we can use kinematics to find the velocity of the center of mass of the tyre. Let's denote the center of mass as point G and a point on the outside of the tyre at the top as point A. Using the formula for the relative velocity from kinematics, the velocity of G corresponding to the center of mass equals the velocity at A plus the velocity of G with respect to A. This second term is equal to the cross product of the angular acceleration and the position of G with respect to A. Note that I've also included x and y axes which show the positive directions that we choose to take. This is going to be important when we come to calculate the relative velocity. We also need the angular velocity of the tyres. Let's assume an engine providing 18,000 RPM translates to the tyre completing 10 revolutions per second. This corresponds to an angular velocity of 62.8 radians per second. Now we have all the information needed to find the tyre's kinetic energy. For the mass moment of inertia, I bar ends up to be 0.5445 kilogram meters squared. To calculate V bar, we need to make sure our vectors match up with the vector diagram. VA to the left is positive and RGA pointing down is negative. For the direction of the angular velocity vector, using the right-hand rule where the thumb points into the page is the positive direction for our coordinate system, but the curl of the fingers corresponds to the direction of rotation. Thus, for our tyre which is rotating anti-clockwise, the thumb points out of the page, and so the velocity vector is negative. After doing the cross product and adding the velocity of point A, V bar equals to 71 meters per second in the left direction. The final kinetic energy of the tyre after subbing in the numbers gives a value of 26.28 kilojoules. Quite a fair bit of kinetic energy just carried by one tyre. Let's also calculate the work on the tyre. To find the work done, we could draw a free body diagram, find the forces acting on the tyre, and do extra calculations. However, the work done on a body in planar motion is actually equal to its change in total energy. As the tyre remains on the ground, there is no change in gravitational potential energy, and with no springs present, no change in elastic potential energy either. So only the kinetic energy of the tyre changes, and since it has zero kinetic energy when starting from rest, the change is just equal to the value we calculated before, 26.28 kilojoules. The benefits of using an energy approach to solving problems allows us to avoid finding any forces on the body, which can get rather tricky. Alright, so that's the end of the video, guys. Thanks for watching. I hope you enjoyed it, I hope you found it interesting, and I hope you got something out of it.